All right, today we are diving headfirst into one of the deepest, weirdest mysteries in all of science. It's called the quantum measurement problem. And really, it's a story about why the universe seems to play by two completely different sets of rules and how we've gotten unbelievably good at measuring a puzzle that, honestly, we still can't solve. Let's get into it.
You've probably heard of this one, Schrodinger's cat. It's a famous thought experiment that gets right to the heart of the problem. See, in the quantum world, tiny particles can be in many states at once. That's called superposition. But if you take that logic to our world, it means a cat in a box could be both dead and alive until we peek inside. Now, we all know that's absurd. A cat is one or the other. So why? Where does all that quantum weirdness go? Why does it just seem to vanish in our world?
And this is the first part of our mystery, right? The missing quantum weirdness. It's like quantum physics. This is the most successful theory in the history of science. It's like it has a secret off switch. And somewhere between the size of an atom and the size of a cat, that switch gets flipped. The difference here is just night and day. Down in the quantum realm, you've got superposition. Particles are literally in multiple places at the same time. But up here, in our world, things are definite. A joke is either funny or it's not. Your keys are on the table, not on the table, and in your pocket. The billion-dollar question is, what is it that forces a choice? What collapses all those quantum possibilities into the one single reality we actually see and experience?
For decades, physicists have been banging their heads against this wall. But back in 2003, a really interesting new idea came along that offered a way out, and it had a name that sounds pretty familiar: quantum Darwinism.
The whole idea is basically survival of the fittest, but we're talking about information. The theory says that any quantum system is constantly bumping into its environment. Photons of light, air molecules, whatever. And every single time it interacts, it's kind of leaking information about itself, making tons and tons of copies that spread out into the world.
Okay, so here's the crucial bit. Not all information is created equal. The weird, quantum information, like a particle being in two places at once, is apparently super fragile. It gets garbled and destroyed as it gets copied. But the stable, classical information, like a particle being in one single definite spot, that's tough. It's robust. It gets copied perfectly, again and again, completely flooding the environment. So according to this theory, when we measure something, we're not actually forcing it to choose. We're just reading the version of the information that survived and won the popularity contest.
Now that sounds like a pretty brilliant explanation, right? It's intuitive. But this is physics, and ideas are nothing without experiments to back them up. And just recently, a really groundbreaking experiment put quantum Darwinism to the test.
And the setup for this experiment is just, wow, it's mind-boggling. Physicists basically built a tiny little universe in their lab. They used 2 qubits, those are the building blocks of quantum computers, as their quantum system, and then they used 10 other qubits as the environment. They could then control every little interaction with incredible precision and literally watch qubit by qubit as the information spread from the system out into its surroundings.
And the results? Well, they were a huge win for the theory. It worked, just like quantum Darwinism predicted. They watched the stable, classical information make perfect copies of itself into the environment qubits, while the quantum weirdness just faded away. It really looked like the case was finally closing on one of physics' oldest mysteries.
But, not so fast, because in any good mystery, there's always a twist. And it turns out, while the experiment was a huge success, it might have been confirming the wrong thing.
Oh, not even close. The issue isn't what the experiment showed. It's what both the experiment and the theory of quantum Darwinism itself completely and utterly failed to explain.
See, the big critique here is that quantum Darwinism, well, it's not actually a new solution. It's more like a super elegant, very complicated description of a process physicists have known about for a long time. It's called decoherence. And decoherence explains how a system loses its quantum weirdness when it interacts with the world. It tells us how the weirdness fades, but it doesn't tell us what happens in that final, crucial moment.
And this quote from physicist Sabine Hossenfelder just nails it. Decoherence takes a particle that is here and there and turns it into a situation that is 50% likely to be here and 50% likely to be there. But think about it. We never, ever see that. When we look, we don't find a 50-50 probability. We find a particle that is 100% here or 100% there. So what makes that final definitive choice? And this is the really big, profound takeaway here. Quantum Darwinism, decoherence,
They do a great job of describing how all the quantum options get whittled down to a set of classical probabilities, but they say nothing about the so-called collapse of the wave function. That's the magic moment when one single reality is actually chosen. And to explain that, a lot of people argue you need brand new physics, something that goes beyond what we currently know.
Which brings us to this really strange, kind of ironic place that modern fundamental physics finds itself in today. It's a place where our technical skills, our ability to build and measure things, has just completely outrun our actual understanding.
I mean, just think about it. We can build these breathtakingly complex little universes on a chip with superconducting qubits. We can control their every move and suck up just floods of data. The technology is absolutely amazing.
And the data we get from these experiments, which cost millions and millions of dollars, by the way, is just stunningly precise. We can track what's happening in these tiny systems with an accuracy that would have been pure science fiction not that long ago. But what are we really measuring?
And here it is, the brutal punchline. All of this incredible technology, all of this stunning precision, it isn't actually solving the deep foundational mystery. We're just getting better and better, more and more precise at measuring the process that we don't understand. We're not eliminating our confusion, we are quantifying it. You know, when you see a number like this, with all those digits, you think, wow, that's precision, that's deep knowledge. But in this case, it represents a deep paradox. We're getting a number that's incredibly exact for a question we don't know the answer to. It's like describing the exact speed and spin of every single wheel on a train, down to the micrometer, without having a clue why the train is on the tracks to begin with. So that's the great irony we're left with. We have total mastery in describing the what, the process of how quantum weirdness fades with unbelievable numerical success. But we've made almost zero progress in explaining the why we get one single result when we actually look. And this leaves us with a really tough and maybe uncomfortable final thought. We pour billions and billions of dollars into fundamental physics, right? From these tiny qubit experiments all the way up to something colossal, like the Large Hadron Collider at CERN. So at what point does getting a more precise number for our own confusion stop being genuine progress? When does science need to take a step back from just measuring the problem with more and more decimal places and start looking for a genuinely new idea? That's definitely something to think about. Thanks for tuning in.